the arc length is going to be the integral from 1 to 2 of the square root of 1 plus the derivative of y with respect to x squared. Right? So we get, right, so that's our general formula for a curve of this type. And so let's see what that gives in this case. So if we take the derivative of y with respect to x and then square it, we'll get the following. Right? So we have that s is equal to the integral from 1 to 2 of the square root of 1 plus, and then if we differentiate y with respect to x, let's see, I guess you'll get x cubed in the first term, and then here we have, let's see, 1/8 x to the minus 2. So I guess you get minus 1/4 x to the minus 3, right, when you square it. No, I'm sorry, when you differentiate it, right, and then that quantity is squared. So the derivative of y, right, is going to be x cubed plus minus 2 times 1/8 times x to the minus 3. So now we have to simplify this. So let's see what we get when we do that. So we get the integral from 1 to 2 of the square root of 1 plus, and then if we square this, right, we'll get x to the 6th, and then we'll get minus 2 times this times this. So when we take the middle term, we'll get minus 2 times 1/4, so I'll give 1/2, and then x cubed times x to the minus 3 just gives 1. And then finally, in the last term, if we square it, we get 1/16 x to the minus 6. Okay? And then I need parentheses. Okay. So when you square this out, right, x cubed squared, you get just by doubling the exponent. The middle term is 2 times 1/4, so that gives 1/2, times x cubed times x to the minus 3. That's x is 0, just 1. And then the last term is 1/16 x to the minus 6. Okay. So now what we can do is combine, right? So now we can combine the 1 in front with the minus 1/2. So this is what makes this work out nicely. Because when we combine the 1 with the minus 1/2, we'll get the integral from 1 to 2 of the square root of x to the 6th plus 1/2 plus 1/16 x to the minus 6. That's dx. Okay. Okay. So we just get a plus 1/2. So now what should we do? How can we simplify that? What would you do now? That's right. This factors, because as you can see, right, this looks almost exactly like this. The only difference is the sign in the middle. So that means that this is going to be a perfect square, just like this was. It's going to be the square of this quantity just with a plus sign in the middle. So all we have to do is rewrite this as this quantity squared if we just change the sign in the middle. Okay? So we can write this as the integral from 1 to 2. And so now what we have, right, is the square root of x cubed plus 1/4 x to the minus 3 squared, integrated with respect to x. Right, because the only difference here is that the middle term has a plus 1/2 instead of a minus 1/2. So this is what we get if we square x cubed plus 1/4 x to the minus 3. And so now, right, again, if you square a number and take the square root, you get the absolute value of the number. Right, so this is going to give us the integral from 1 to 2 of the absolute value of x cubed plus 1/4 x to the minus 3. Okay. But of course, since x here is positive, we can just drop the absolute values, okay, since we're looking at positive values of x. And so we get the integral from 1 to 2 of the quantity x cubed plus 1/4 x to the minus 3. Okay, and so now, because x is positive, right, we just drop the absolute values. And now, if we integrate, we'll get 1/4 x to the 4th. And then here, right, if we divide, if we add 1 to the power, divide by the new power, we'll get minus 1/8 x to the minus 2. You'll notice what we have is almost what we started with, right? It's almost exactly what we started with. It's 1/4 x to the 4th minus 1 over 8 x squared, right? Evaluated from 1 to 3. So now we just have to evaluate this. Let's see what we get. We get, let's see, I guess we get 81/4 and then minus 2. Okay, and then minus the value of 1, which would be 1/4 minus 1/8.
Yeah.
Oh, it's 1 to 2. Oh, okay, I'm sorry. Yes, sure is. All right. So it's 1 to 2. So let me try that again. So, so this is from 1 to 2. So let's see. So when we substitute 2 in for x, we'll get, let's see, so we'll get 4 minus 1/32. And then at 1, we'll get 1/4 minus. Thank you. Okay. So let's see. That'll give 4 minus 1/32 minus 1/8. So we get 4 minus, let's see, so we have minus 5/32. So I believe we get 123/32. I think that's right. Let's see. So the basic idea of this problem, and there are other problems like this, is that when you take the derivative and square it and add 1, it just changes the sign in the middle term. So you still end up with a perfect square. Okay, when you do that. Okay. Does that look all right, what we've done so far? Let's take a look at another example. So let's look at the following curve. So let's find the length of the curve y equals x to the 2/3. Okay. So let's find the length of y equals x to the 2/3. And let's see, here, I'm going to let's let x go from 0 to 5 square root of 5. Okay, so x is between 0 and 5 square root of 5. So to find the length of this curve, we could actually use either of these formulas. Okay? In fact, right, it might look most natural to use the first formula there. Right, where we just take integrate the square root of 1 plus dy dx squared. But in this problem, it's actually easier to write x in terms of y, and then use this formula. So that's what I'm going to do here. So I'm going to switch the roles. In other words, I'm going to solve this for x in terms of y first, and then work this out. And you'll see that that's actually easier than just doing this the way we did the last example. So instead of working this the same way we did the last example, I'm going to first solve for x in terms of y. So if we do that, right, we get x is going to be y to the 3/2. And let's see what the value of y would be. So when x is 0, right, y is going to be 0. And when x is, right, this is 5 to the 3/2. So when x is 5 to the 3/2, y is going to be 5. So I'm going to rewrite it in this form, and then use the formula that we have here. Okay, so let's do that. So if we use this formula, we'll get that the arc length is going to be the integral from 0 to 5 of the square root of 1 plus dx dy squared, integrated with respect to y. And so that'll give the integral from 0 to 5. And we'll have the square root of 1 plus, so if we differentiate x with respect to y, right, we get 3/2 y to the 1/2. So we have 3/2 y to the 1/2 squared, integrated with respect to y. We get something like that. So now, right, if we simplify that, let's see if that gets. So we have the integral from 0 to 5 of the square root of 1 plus 9/4 y. And now, right, it's not too hard to finish. So what we could do at this point, right, is just substitute for what's underneath the square root. Right, and that would work because the derivative of this expression is 9/4. So at this point, we could let u equal 1 plus 9/4 y. Let me just to avoid working with fractions, let me just simplify a little bit. or so, okay, and then to make a substitution. So let's just write this the following way. So we write this as the integral from 0 to 5. So we put this over a common denominator, right, we get 4 plus 9y over 4 dy. And then if we just write that as the square root of 4 plus 9y over the square root of 4, we can write that as 1/2 the integral from 0 to 5 of the square root of 4 plus 9y. So I'm just doing this just to avoid working with fractions, just to make it a little bit easier to calculate. Okay. So if you wanted to, you could just substitute u equals 1 plus 9 plus y right there. But now let's substitute u equals 4 plus 9y. And then du is going to be 9 dy. And if we change the limits, right, if y equals 0, we'll get u is equal to 4. And if and if y is equal to 5, we'll get u is equal to 49. So those will be our new limits. So we can write this as, let's see, we need to divide by 9 on the outside and multiply by 9 on the inside. So we'll get 1/2 times 1/9 the integral from 0 to 5 of the square root of 4 plus 9y times 9 dy. So if we write this in terms of u, right, we have 1/18 the integral from 4 to 49 of the square root of u du. Right, square root of u du. So we have 1/18 the integral from